In lesson 9.4, we are going to be learning how to graph ellipses. So you can see the objective. We're going to learn about a couple specific features. That is the center, the foci, and the intercepts of an ellipse. And we'll also talk about the general equation. So first of all, what is an ellipse? You can see the formal definition there. It says an ellipse is the set of all points P in the plane such that the sum of the distances from P to two fixed points is a given constant. I'm going to have this be animated in class. It's a little harder to show on this video, but think of these 2 points here as being fixed, and think of this as being a string. Then if you took your pencil with the string and moved it into a circle, again, it's like the string is nailed down at those 2 points, you would make an ellipse. So it says the center of an ellipse is the midpoint adjoining its 2 foci. Those are those fixed points. The major axis of an ellipse is the chord passing through its foci. The major axis is the long one. So see how this is like a short and fat ellipse in this case? The major axis would be the x-axis, meaning it's longer in the x direction. The minor axis is the chord containing the center and perpendicular to the major axis, meaning in this case, since it's short and fat, again, the y-axis is the shorter axis, so that's the minor axis. So here's the equation of an ellipse. You can see it's here. It's x minus h squared over a squared plus y minus k squared over b squared equals 1. The center is still hk, so we've seen that similarly with graphing circles. Now, we need to think about the major axis and the minor axis, and this is going to depend on these values of a and b, which we won't really look at the letters a and b. We're going to be looking for which of these denominators is larger, though. So, the length of the major axis, first of all, is 2 times the larger denominator. The length of the minor axis is 2 times the smaller. These things are all kind of just definitions laid out, and then they'll make more sense when we actually do a problem. Those focal points, or the foci, is the distance from the center along the major axis. So those are those 2 fixed points we saw on the previous page. And the way to figure out that that focal point distance is to use this equation, which is the square root of the big denominator minus the small. So again, I'm not using a and b because we're just going to be looking for the larger and smaller denominators. So this is all going to make sense when we do our examples. All right, well, the first example is not going to require any graphing. So it says write the equation in standard form and then determine if it's a circle or an ellipse. Well, in both our equation for our ellipse, you saw that it was always equal to 1. So let's go ahead and get this equal to 1 on the right-hand side by dividing by 144 on both sides. So dividing by 144 on the left-hand side means you're dividing both the 9x squared by 144 and the 16y squared by 144. And then obviously on the right-hand side, 144 over 144 is 1. So if we reduce the first fraction, 9 over 144, we're just going to get 1 over 16. If we reduce 16 over 144, we're just going to get 1 over 9. So this is an ellipse. It's in that general form of an ellipse. If we think about the previous slide, we know that there were those parentheses. It was x minus h squared, y minus k squared. But you could just think of those as being zeros in this equation. And then we have denominators of 4 squared over 3 squared. This is in the general form of an ellipse. Let's look if we try to do the same thing for example 2. Let's say we try to get this equal to 1 on the right-hand side because we're thinking it's going to be an ellipse. So that's going to be 3x squared over 75 plus 3y squared over 75 equals 1. So if we reduce here, we're going to get x squared over 25 plus y squared over 25 equals 1. So far so good. It kind of looks like it could be an ellipse here, but this is where I want you to see the difference between these two problems. Now, for the ellipse, if we look back here, the larger denominator, so the 4 squared, is underneath the x. What that means is x is the major axis. If I made a really rough sketch, the x-axis would be longer in this direction than the y-axis, which was only a denominator of 3 squared. So that's why we know it's an ellipse, because one of the denominators is bigger than the other. If you look here, the denominators are equal. If you think about it, that would be saying, you know, go equal in the x direction as it is in the y direction. So if we have an equal in all directions, what is that? That's the radius of a circle. So this is actually the equation of a circle. So if we go ahead and just multiply by 25 again on both sides, we'll get it into that general equation of a circle. So x squared plus y squared equals 25. Remember, that's in the form x squared plus y squared equals r squared. So the moral of the story for this problem here is that circles would have equal denominators, whereas ellipses have unequal denominators. Okay, so here's a problem. Graph the ellipse. So we can see the equation of the ellipse here, and it's basically in general form. So I can rewrite it underneath the graph here, but we have x plus 3 squared over 16, which I'm going to just rewrite as 4 squared, plus y minus 5 squared over, I'm going to rewrite 9 as 3 squared, equals 1. So that's in that general form. I'll rewrite the general form underneath it just so you can compare. We can call this a and b, but that part's not that important. Y minus k squared over b squared equals 1. Okay, to find its center, that's our hk. So we're looking at the terms within the parentheses here. So if this is x minus h, then our h in this case is -3, and then our k is +5. So that's the center of our ellipse, -3, -5. Okay, let me zoom in and get that. Or sorry, -3, +5. 1, 2, 3. So there it is. Okay, great. So now what we're going to do is use the denominator to plot what's called the vertices. So 4 points on the ellipse. This is very similar to the radius, but like we said, there's unequal denominators, so you're going to be going an unequal amount in each direction. So look at the number underneath the x-axis. That tells you how far to move in either direction in the x direction. So if the denominator in that case is 16 or 4 squared, what that tells us to do is we can use this 4 and move 4 in the x direction. Again, because 4 is underneath this x term here. So it's like the radius in the x direction is 4, is kind of an easy way to think about it. So I'm going to move 4 to the right and 4 to the left from my center and put 2 points. So 1, 2, 3, 4. 1, 2, 3, 4. And that's going to be my major axis, my longer axis, because in the y direction, our denominator is 9, so that's 3 squared. So 3 is the amount that we're going to move in the y direction. That's going to be our minor axis. So I'm going to go to my center and move 3 up and 3 down. So really at this point we have enough to make our ellipse. But this question also asks for one other thing, and that is to find the foci. Okay, the foci are points that are just equal distance from the center, and they're inside the ellipse. So I'm picturing something like right inside of here. Now we need to be able to use the equation to find them, which, if you remember from the previous slide, is always the square root of the big denominator minus the small. So in this case, that would be the square root of 16 minus 9, and that's the square root of 7. So the square root of 7 is what we're going to move in either direction. Now you might want to put the square root of 7 in your calculator just to get an idea for yourself about where that actually is, and it's about 2.6, so about 2.5. That's the direction we're going to move from the center. So I'm going to go to the center and move 2.5 to the right, and then put a point, and then 2.5 to the left. So let me do that. 2.5, so 2.6, and then 2.6 to the left. So those are our two focal points. So if I was to write what those points actually are, which I want to do right here, we went from the center, which is -3, 5, but in the x direction we went plus or minus √7. You might be asking, well, why did you go in the x direction? Why didn't you know to put your points 2.5 up and 2.5 down? The focal points are always along the same axis as the major axis. So I went to that longer axis and went in that same direction. And now we have everything we need. We have our ellipse graphed with its foci. Let me zoom out a little bit so you can see everything at once. There we go. All right, let's try another. As you can see, and what you've seen in all of these conic section graphing problems we've done, is that the way these problems can get a little bit longer is by not giving you the formula in the correct general form. Now, same as before, if we want to get this into the form x minus h squared and the y minus k squared, we're going to need to complete the square. So we're going to do the same thing here. I'm going to start this problem kind of underneath the graph to show the algebra for completing the square to getting it into the general form of an ellipse. So here's the original problem. Again, we want it to be in the form x minus h squared and y minus k squared. So we're going to complete the square with both our x's and our y's. So I'm going to rewrite the x's next to each other and rewrite the y's next to each other. This will feel really familiar to when we were working with circles. And I'm going to move the constant to the other side. Remembering whatever I add to one side, I have to add to the other. Now you can notice here with our 4x squared that we need to have that coefficient be 1. Again, this is all exactly the same as a circle so far. Coefficient of our y squared is already 1, so I don't need to worry about that. Okay. So what goes in here is our b over 2 squared. So our b in this problem is just this 1 right here. I'll try to write it real tiny under here. So that's 1 over 2 squared, or 1/4. Whatever you do to the one side, you have to do the other. Remember, that's 4 times a fourth, so you're actually adding 1 to the other side. Then you do that for the y's, so this is -4 over 2 squared. So that's -2 squared, or 4. Whatever you add to one side, you have to add to the other. So we have is 4 times the perfect square, x plus 1/2 squared, plus the perfect square, y minus 2 squared, equals 11 plus 1 plus 4, or 16. Now the last thing to do is remember that ellipses are always equal to 1. So what I'm going to do is divide by 16 everywhere to get that piece equal to 1. So let me show that final step just over here. So look this way. So if I reduce the 4 and the 16, I'm going to get that term x plus 1/2 squared over 4 plus y minus 2 squared over 16 equals 1. And that's our general form of the ellipse that we're going to work with. You can see your center is HK, so that's, so let me just write here, step 1, see below. Find the center, so that's HK. So we have -1/2, 2. Those are the terms that are inside the parentheses with the x and the y. Now we're going to use the denominators to plot the vertices. So I can see already that since the bigger number is underneath the y-axis, I'm picturing a tall and skinny ellipse. The major axis is the y-axis. So let me first plot my center at -1/2, 2. So -1/2, 2 is right here. Okay, and then let me use my denominators to go ahead and plot those vertices. So the denominator, try to color code this again, the major axis is going to be the y-axis, and the denominator is 4 squared, or 16. So what that tells me is I'm going to go 4 in either direction in the y direction. That'll be my major axis. And then in the x direction, I'll use my denominator of 4, which is 2 squared, meaning I'm going to go 2 in the x direction in both directions from my center. So let me do that for us. So in the y direction, I said 4 in either direction. So go up 1, 2, 3, 4, put a point. Go down 4, 1, 2, 3, 4, put a point. And then in our x direction, our denominator, we're going to go 2 in either direction. So 1, 2, 1, 2. So now we have what we need to make the ellipse. Like I said, the major axis is the y-axis, so it's one of these tall, skinny ellipses. I clearly managed to miss both of those points that I was supposed to hit. Let me try that again. Make it a little better. It's hard with this iPad. Okay, you get the drift. So now the last thing I need to do is get those focal points. So focal points, remember, we get using the equation. I'll try to use a different color. The square root of the big denominator minus the small. That'll tell us how far to go from the center. And we know that this is going to be in the y direction because it has to be the same as the major axis. So it's the square root of 16 minus 4, which is the square root of 12, which reduces to 2 root 3. Again, we're going to be moving from the center, which is negative 1/2, 2, but now we're changing the y direction. We're going up and down in the same direction as the major axis. So that's how we list our focal points. So let me go ahead and plot those points. We know that you can use your calculator if you need to, but 2 root 3 is about 3.5 basically, so 3.5. So I'm going to go in the y direction 3.5. 1, 2, 3.5, so it's just inside there. And 1, 2, 3.5, so just inside there for our focal points. And that's it. You've graphed everything for your ellipse. Last example, example 5, it says find the equation of the ellipse having the given points as foci and the given number as the sum of the focal radii. So we are going to introduce one new equation here that will help us with that idea of the sum of the focal radii. So let's start with what we're trying to do, which is write the equation of an ellipse. So I'm going to write down that general form. Okay, I'm leaving the denominators blank for a second because we're going to have to think about like which denominator is going to be the larger denominator and which one's going to be the smaller denominator. So let's put what we know on the graph. Those 2 points are focal points, the point 6, 0 and 6, 6. So let's get those on there. So 6, 0, 1, 2, 3, 4, 5, 6, and then up 6, 1, 2, 3, 4, 5, 6. So if these are my focal points, I automatically know where my center is, right? Because the focal points are always an equal distance from the center in either direction. So I can go ahead and put my center right here, which is equal spacing 3 and 3 from my focal points. So right away I know that my center is going to be at the point 6, 3. So that'll fill in my HK. So let's put that in there. Again, I'm still going to talk about the denominator in just a second. So x minus h squared plus y minus k squared. Okay, so also we know which axis now is the major axis because the focal points are always along the major axis. So we know that because these focal points are lined up in the y direction, that we're going to have a tall, skinny ellipse, and the major axis is going to be the y-axis. So we'll call these A and B again, but let's define A as the larger denominator. And again, we know that because the focal points are along the major axis. So now it's just a matter of getting that A and B. So here's where we're going to introduce a new equation, which is this idea of the sum of the focal radii. The sum of a focal radii can help us get this A, that the denominator of the larger denominator that's along that major axis. So here's the equation. The sum of the focal radii, where should I write it? Maybe over here. Sum of focal radii in this problem is 18. That's always going to be equal to 2 times a, where a is that larger denominator. So just by dividing by 2 on both sides, I get that my a is 9, and I can go ahead and plug that in. So right now I have x minus 6 squared over b squared plus y minus 3 squared over a squared, so 9 squared, equals 1. And then the last thing we need to do, I'll switch up my color one more time. Now we need to find the b. So the way that we can do that is say, oh, well, I know that when we do this whole idea of finding where the focal points are, we say, oh, well, I know that the distance I need to move is that square root of the big denominator minus the small, right? So the big denominator we already know is that 9 squared. So we have the square root of the big denominator, which is 9 squared, minus the small, which is what we're trying to find, equals, and then, what is that distance actually equal to? Well, we already know it. We already talked about it. It's 3, right? It's that distance from the center to each of the focal points. So it's 3 away from the center, so we just set that equal to that 3 that we saw from our graph. And now we solve this. So I'll go ahead and square both sides to get rid of that square root, and I'll get 9 equals, square root goes away. We know 9 squared is 81 equals negative b squared. I'm running out of room a little bit down here. But if we do the 9 minus 81, get rid of the negative, we're going to end up with 72 equals b squared, or b is the square root of 72, but we're just trying to put something in for that b squared denominator. So maybe if I scooch this up. So putting it all together, we have the equation x minus 6 squared over b squared, which we just found is 72. Oop, pen. 72. Plus y minus 3 squared over 9 squared, which I'll just rewrite as 81, equals 1. So that one's really like a puzzle. You kind of need to sketch a picture of what you already know so you can get your center, and so that you understand the spacing, the distance from the center to the focal points. You have to use this new fact that the sum of the focal radii is equal to 2 times your larger denominator. Your larger denominator is going to be that major axis. So this one is a really good problem that kind of tests your understanding of how ellipses work. Alright, that was lesson 9.4. You can go ahead and take a look on Schoology for that homework.